So we have completed two items. Now we look at strain energy due to torque stored in a uniform circular shaft. So if you look at this diagram, you will see that there's a shaft in which a torque T is applied, and there's a torsional deflection theta, and the length of the bar is L. So theta is the angle of twist one end of the shaft relative to the other. T is the torque applied. L is the length of the shaft. So the work done due to the strain energy of applying a torque is basically half times force and the deflection. So the force is actually a torque, therefore it is half torque into the deflection. Okay, that is theta. So it is half t into theta divided by half, or ut. However, you can look at that the T divided by J, which is equals to shear stress of the shaft due to the applied load, that is tau, divided by R, which is equals to torque divided by the polar moment of inertia, which is equals to G theta divided by L, which is G means the modulus of rigidity, theta is the deflection angle, L is the length of the bar. So now you can take theta to one side, and therefore theta equals TL divided by GJ. So you can substitute for the equation ut as half t theta, which is equals to half t into TL divided by GJ. So the total energy of a deflection due to torque is T squared into L divided by 2G theta. So we will see an example determining the maximum deflection of the end-loaded cantilever beam below using an energy principles. So we will consider a cantilever beam which has a length of L and deflection of delta. We will consider from the weighted load point to the x direction, x value. So we take a random length x at from the far end of the point load, and the length is L. Let M be the bending moment, I being the moment of inertia, E is Young's modulus of elasticity, delta is the free end vertical displacement. So from the earlier equation, we can take UB equals m squared divided by 2EI dx. So for the whole length, it will be integrating from 0 to L length. But now if you look at the previous diagram, the moment at x is basically minus w times x, because the force is w and the distance is x, therefore it is w times x. So if you integrate the energy, minus w squared divided by 2EI integral of L into integral from L to 0, which is x squared dx. So after integrating x squared, that is the variable which we take it from L to 0 length. Therefore the total bending moment, total strain energy due to bending is equals to minus w squared L cube divided by 6EI. So now if you take the work done by the load is WD, which is equals to half W into delta. Since work done is equals to UB, which is the energy, strain energy in the beam, so therefore we can equate it to taking as half W delta, which is equals to minus W squared L cube divided by 6 EI. So after taking to one side, you can see that the deflection is equals to delta, which is equals to minus W L cube divided by 3 EI. So we will talk about to determine the midspan deflection of the centrally loaded simply supported beam below using an energy principles. So there is a point load applied on the center of the beam, which is W, and you take an x direction from one direction, from one end. You take a random x length, and for that we have to apply a load. So now if you look at the solution, the strain energy UB, which is equals to integral m square divided by EI to EI dx. But if you look at the previous picture, you can basically the W weight is is if you take from one end A, the reaction force acting on the W is basically the reaction force acting at A point, which is equals to half W time half W, the reaction force. So if you take the moment at in x direction, the moment will be only applicable through the A end. So the bending moment is basically minus W into x divided by 2. So m is equals to minus W divided by 2x from 0 to L divided by 2. So if you integrate m squared divided by E2EI dx, so m we have to apply minus Wx divided by 2, which is squared, and after integration we can get the solution as minus W squared L cube divided by 96 EI. So now if you take the work done by the load, which is equal to half W times delta, so work done is half W times delta, which is equal to minus W squared E L cube divided by 96 EI. Solving for delta yields delta, which is equal to minus W L squared divided by 48 EI. So we will talk about Castigliano's theorem in the next chapter.